All right, welcome back. New week, new stuff to learn. Hey, did you read the chapters, I don't know, about Bellman equations and value functions and all that? Everything is super clear. I'm gonna make it muddy. This is a good thing. I don't know. I will try not to make things muddy, but I have some arguments with how things are done in the book. If you're reading very, very carefully as a mathematician would read things, and you might feel that some things are a little bit underdefined. So I try to be more precise because later on, I will ask you to do calculations, and like for that we need precision. So today, I wanted to also think about the whole week. So for the whole week, it's just going to be these Bellman equations, Bellman ultimate equations, whatever. And then there's a quiz too. The quiz that was last week's quiz, it was a practice quiz. It had no deadline. It was a Coursera thing that it had no deadline. We were still figuring it out, like how it's going to be marked, but like we're going to be generous, and like if you haven't done it, do it like before the end of this block, and marks are going to show up. Hopefully, we'll figure it out soon. That's what the quiz. The practice quiz for this week does have a deadline, of course, there, and it's Tuesday. And then there is another quiz that's due at the end of the week by Saturday. All right. And okay, so without further ado, we're back to MVQN and back to our famed finite MVPs. We have a finite state space, finite action space, finite reward space, because we love finite. And we have a transition function, or kernel, or whatever, like many names. And I think that last week I was using uppercase P, and then now I'm noticing that in the book it's lowercase. All right, so those are fine. I think that there are historical reasons why people use uppercase, and sometimes, but this is also a probability mass function or conditional probability mass function. So lowercase is totally justified for that, according to the standards of probability theory. So what is this function? It takes 4 arguments, takes a state action pair, and returns a reward and an exit. Okay, the other thing, the ordering of that 2 arguments. I think because in the history, when we write the history for our whole process, then we tend to write state action, the reward, next state. I like this ordering because then I don't have to flip the ordering between the reward, the long transition, and the state, right? So when we were writing about the Markov property of this history process, where you have states, an action, you have a reward that is incurred as a result of using this action in this state, and you get a next state. Here the ordering is reward and next, and not the other. I mean, like, it's a combination. But I like to be consistent. So since here, and the book also uses this ordering for that, here this is the ordering. I want to use that ordering. But it's like, if you flip it, okay, I will understand it, right? It is, if they flip the argument and like some solution. As long as it's clear that what's going on, it's good. All right. So when you have this four tuple, and the book slams in a gamma, and like, oh, let's talk about the gamma is part or not. It's a minor factor. But when you have these things, let's give it a name M. There may be MVPs or model or whatnot. It models the environment that you're interacting with. So this M together with a way of acting, we talked about this a lot, induces a probability distribution, and you also get the sequence of states, actions, reward, next states, and then it continues, right? So the next action, next reward, next state, and then repeat. And so, of course, these are unknown variables. So you have a sample space, omega, and from this sample space, these are mapping to this humongous product space of all possible states across all possible actions, across this all possible rewards, across this all possible states, and so on. This infinite product. And they also come with this P, this probability distribution that is put over omega. Okay, so that's a probability distribution over omega. And okay, there are some rules to this, how this must look like. So the idea is that you have this environment. This is modeled with M, with this transition curve. And you put here something that sends the actions. And as a result, it gets back the state. So the state is updated here. But it gets back, as a result, the reward and the next state. And as a function of what it gets back, it can produce a new action. So this box, this is for what we write the code for, learning algorithm or whatnot, or just like a fixed map that maps, I don't know, the last state to an action, maybe deterministically, maybe stochastically, maybe it takes into account a history of states. Last week was all about, like, do we need the history? Do we not need the history? When you learn, when you have a learning algorithm, it learns about this unknown model, and it uses all the history to learn maybe a model, and like it uses all the history. So in general, you have here something in this box that computes a probability distribution over the actions given everything that happened before, given everything that that box has ever received. And so there are various things. So we were, I would say there's a causal action selection strategy or something like that. But it goes to different names. Some people just call it policy. But that needs a little bit of clarification, because the book also uses the word policy. But the way the book uses the word policy is just for some very specific policies. Those are the policies that normal people call, or like the rigorous mathematician type people call, memorized policies. Those are the policies that just...
There's an echo, I'm seeing.
Oh no. So you resolve that. So those are memoryless policies. So the book takes it for granted that all the policies that it's talking about in the chapters you're reading, they're memoryless. I'm going to go a little bit beyond this, because in general, you could have policies that remember the past, and then sometimes it's useful, sometimes it's not useful. Actually, it's a question that if you have an MDP and you're observing its state, but it's going to be useful to remember anything from the history or not if you know the MDP. Even if you know the MDP, maybe the history could help you. If the observations are not the state, we have seen the example, pick and place. In the pick and place, when the observations were not the full state of the internal state of the system, then we wouldn't be able to just write a function that tags the last observation, because it might be missing information like whether the robot is holding an object in its arm, and when it's at the add position, and it doesn't know whether an object is in its arm, it doesn't know whether it should go back and pick up an object, or it should just drop the object that it is holding or not holding. But if it can remember that, oh, I picked up because every time I go to the start position, I can pick up something, then with memory, it can do a good job, right? Like then there is no problem. So memory can be useful. And so one question that you might have is whether memory is useful if you have an MDP and you're observing the states. And okay, breaking the big tension, no, in that case, memory is not going to be useful. That's like a big theorem that we're going to show that like memory is not going to help you if you have an MDP and you're observing the state of the MDP. So that kind of means that when we are writing future like algorithms for here, we don't have to worry about if we observe the state to kind of discover what to remember. You don't have to worry about that. The memory can be used for, if you don't know the MDP, for learning about the MDP, collecting statistics and whatnot. That's also some kind of memory. All right. Anyways, so there is memory-less policies and policies which use history. So sometimes those policies are called history-dependent. All right. So the book is not going to tell you that this is more memory-less. By the way, there are other names. It's like, I don't know. I don't want to overload you with that. But some literature calls this stationary Markov policies, because we love Markov. So Markov just means that in this case, in the case of policies, it just means that it looks at the state and then it decides what to do. But it could be non-stationary. That means that it can say that like in time step 2, I want to do this if I see this state. But in time step 3, I want to do something else. So it's like there is a stationary, there is a non-stationary Markov. It's a complicated notion, and I'd rather just go with memory-less and history-dependent. And usually it's going to be clear from the context which of these guys I'm talking about. In the book, if they say policy, it's definitely just memory-less. Okay? For me, it's like, oh, if it's not clear, then you should ask. All right, so formally, what is a history-dependent policy? Because that's the more general case. Well, the history-dependent policy needs to decide about actions given the history. So we have to build up history. So the history at time step 0 is just all possible states, because you start with observing a state, and then you can make a decision about what you want to do. So if at that time step I have to make a decision, I could just like map. I'm going to introduce this notation age of t to denote the set based on which, but that contains the thing based on which I need to make a decision, like the states here. So here at time step 0, I need to make a decision based on the state. What's the decision? Well, it's going to be a distribution over the actions, because that's general. Maybe I'm randomizing. Epsilon grade is randomizing. Maybe it's useful to randomize. Who knows? Like, we should allow randomizing. So that's what happens at time step 0. Time step 1. So basically, you're here. You first somehow manage to get a state. You make a decision. You send it over. you get a reward in the next state. All right. So next time, you also have a reward. Oh, not only that. We do have our action that we took, and that's part of the history. Why is that important? But it's only important if we're randomizing. If we're randomizing, then it's super important to know how the dice ended, because like if you want to learn based on past information, you better know what action you actually took in the last time step. It was random. So if you don't remember it, it's hard to associate what information you're receiving with like what was supposed to happen. So the action becomes part of the history, and then we get a new reward, a new state, and we need to return a distribution. So that's how you can make a decision at time step 1. So now this product space is getting longer and longer. So I better introduce some more organized notation. So I'm going to call HT minus 1 cross whatever I wrote here. The action, the reward, and the space. So this history spaces grow. So this starts at t equals 1, and so on and so forth. And then generally you can write that the policy is going to map an element of the history, possible history up to time t, whatever is known to the policy at the time t, to a distribution over the actions. Right? Just notation. So many times I would just write, okay, you have a history from the space, and pi t processes the history. What is this? This is a distribution. I can sample from this distribution. Other people would write, that's syntactical sugar, if you wish, something like this to denote the distribution. It's like there's this parenthesis, the bar, the dot, because it looks like it's a conditional distribution given the history over the actions. But it denotes the same thing, right? The particular value is that, okay, so this dot stands here for that you could write an action here. And then this would be the probability of choosing A given HT. That given that we have seen HT, this particular history, this is the probability for this action. And then whatever is sampling the actions, it solves how to sample an action from that distribution. All right. So this is history-dependent policies. So you can interconnect a history-dependent policy with an MDP, and that gives rise to this distribution P. Except that something else is missing, which also came up last week, miraculously, in our discussion with pick and place, which is the distribution over the initial state. All right, so what's the initial state of the process? How does the MDP start? What's the first state? Okay, zeros state, actually. So in general, the zero state could be chosen. So we have this pi, which is a history-dependent policy. And this S naught could be chosen from some distribution, which is a distribution over states. And whatever way you start, then the initial distribution, after that, you take the action that is dictated by the policy. Then the word moves and gives you a reward in the next state. That comes from the MDP, this transition function. And then after that, you continue with your policy, which now reads all this history. So that's going to be the history up to that time step. And it spits out the distribution of reactions from which you sample another action, and so on and so forth. So if you continue this way, and you can see that you can continue this way, that completely specifies a distribution over all possible infinite sequences of states, actions, rewards, next states. Okay? Let's write it down, because how do we know that we're talking about the same thing unless we wrote down what we mean by this? Okay? So this, what is this distribution? So if you want to specify a distribution over an infinitely long sequence, then I'm telling you there is a powerful result that says that it's enough to specify these probabilities for all prefixes, okay, of finite length. You don't have, I mean, like, it's like just an extension, right? So it's like you continue that way, and then it all works out. You get a probability distribution over the infinite space, right? They have to be consistent with each other, but in this case, lo and behold, they are, because the whole thing should make sense. So, all right, so how do we do this? So what is the probability distribution? How do you specify a probability distribution? Well, it's an infinite sequence, so let's just like cut it at some time t. So maybe you go up to, I don't know, where do you want to cut it? You can cut it here, you can cut it here, you can cut it here. You can cut, where do we cut it? After the actions, after the rewards, after the states, where should we cut? You tell me. It won't matter. Except that I wouldn't cut here. It's kind of weird to cut between these two because these come in pair. So we do have two choices where to cut. Like we can cut here or we can cut here. After an action or after a state. Which one? Okay, who wants to cut after actions? Cut after actions, one vote. Cut after states. More popular. Cut after states. All right, okay. So thank you so much for cutting after states. Because that means that I can just use these spaces, right? Because they finish with states, right? So I can pick a history. So I can pick a length. So that's the cut point. And I can pick a history from this space. Okay, let's see. We have to match. We have to check whether the indices match, because I just arbitrarily finished that like RT-ST, but I don't actually know whether that's RT plus 1 or ST plus 1. This is one of those edge conditions, right? So how do I do that? Well, I check H1. So H1 should have 4 elements. So when t equals 1, then I should finish here. That seems about right. That's at ST. All right. Okay. And now, all right, I'm going to introduce this capital HT just to save some writing. So this is the random history. All these random variables. So basically the same thing with uppercase letters, right? So I collected all these random variables into just like one more random variable. I call it HT. It will allow, hopefully, me to save some space. I'm not sure. We'll see. And then we want to write what is the probability of HT equals HT. And now we are just going to, what? Yeah.
Just a quick clarification. Is this a general case or is this specific to MDP?
What we are doing is really specific to MDPs. At one point you will see, and then maybe we come back to that point, and then we can discuss the general case. So basically, now what we're doing is that I gave you for the first time this probability distribution that appears everywhere in the book and other books, but it's never defined. But you are supposed to understand it the way I'm writing it here. And once I write it down, it will make sense. And you would say, yeah, okay, that's pretty obvious. It just takes a little bit of time to write it down. I think that that's why people, and it's also because it's pretty obvious, people don't necessarily write it down. Yeah.
So if it is the case of an MDP for our history at time t, why do we care about everything from the start except
when we are choosing the policies?
Yeah.
Because we want to be able to answer the question, should we care? And if I never wrote the case when we are caring, we wouldn't be able to answer this question, to which the answer is going to be no. If you only care about whether you can act optimally or not, then the answer is going to be memoryless is your friend. You can always achieve what you can achieve with history-based policies with a memoryless policy. That will be a big theorem, but I won't be able to say the big theorem unless I first introduce that, oh, you could care, and actually in other situations where you're not observing this, that's how your question is, the previous question is connected. In other situations, you definitely do need to care. Okay, right. Okay, so this is a definition. It's not, nothing is following now from, like other things that you're supposed to know. I'm just defining things. But I'm going to define it in a nice and consistent fashion so that everything makes sense. So what is this? So this HT, it has all the states, the actions, rewards, ends, and so forth. So we need to calculate a number between 0 and 1, which gives you what's the probability of this. What is this? Well, the first state is S0. And so this HT equals HT. If you expand it, it asks the question, what's the probability that the first state, S0, first random state, is equal to this particular state, and at the same time, this action, the first action, is equal to this particular action, and so on so forth up to the end. What's the probability of that thing, of that event, that's happening? And so now I'm going to tell you what is this probability. It's a number between 0 and 1. This is the definition. So I'm going to write this number. So the probability of seeing, so we go step by step. Like if I was stopping at cutting off stuff at time 0, what would be this probability? Couldn't possibly be anything else if you're sensible about what we are saying, is that it has to be the probability that is assigned by mu to S0, because otherwise, what are you talking about? Like, what is this doing? The job of this is to design what's the probability that the S0, capital S0, takes on the little value of S0. It has to be mu of S0. By the way, do you guys see this? Or like, it's not visible? It's good? Yeah? Okay. All right. I'm worried because it's like there are kind of abstractions. Anyways, all right, so that should make sense. So next thing, what's in the history? This action. What's the probability that A0, capital A0, is equal to little a0? What should that be? Well, for that, we have a policy that takes care of that, right? And so the policy is the one that's computing these probabilities that you're going to get for various histories. So we have a policy for time type 0. It's called pi0. And it takes 2 arguments. One argument is the action whose probability we are asking. And the other is like, it's after the bar, syntactic sugar again, is what's the history up to that point? What's the history? It's like just S0. It's just the state that the policy or the agent sends. Right. So proceeding further, what's the probability that we see some reward? Well, let's take these two guys together because they are really together. You're seeing some reward and you're seeing some next state. Where is that coming from? What do you think? Where is that coming from? Is it coming from the policy? Be brave. Real question. Yeah.
Should be V1, right?
There's no B1. That was just initial state.
Oh. It could be U again, but some other different thing depending on.
There's no more mu. I'm telling you that this probability distribution is going to be determined, and that's why I have multiple markers here. The initial distribution, the policy. Okay, so I didn't write what the policy is, but the policy is really this whole sequence of pi 0, pi 1, and so on and so forth. Like for every time step, we have this probability distribution over reactions given a history. So in short, it's just like pi t, where t is from 0 to infinity. So that's the second thing. So this and this was the third thing that determines this probability distribution. Yeah, like here, yeah. Somehow pi lives here, mu lives here, and another thing lives here. This transition cutoff, right? So that's the third thing. And it's kind of like just understood that we're interconnecting this policy with this word whose law of dynamics is described by P, right? Okay, so what corresponds to this capital R1 and S1 is the little r1, little s1 that's matched. So P R1, S1, given what? What should I write there? Okay, I'm hearing given S naught, A naught, and that's correct, right? So the word is reacting to like what its previous state was and what was the incoming action, and it's spinning out a reward and a next state. And continue this way. All right, I have, I'm just going to recklessly continue here. So let's write the probability of this guy because that's the one but last thing. And after that, we will just have the reward and the state. So it's like we write these two last terms, and from that, you will see the pattern. So these probabilities are multiplied together, okay? So what's the probability of seeing this action? Yeah. I hope that that's just called ht minus 1. It is. So no, I saved a little bit by my notation of histories, but they're just like expanding, you know, everything up to this thing, but t minus 1 here, right? And so that would be st minus, that ends with st minus 1. Okay. And what's the probability of then seeing this reward coming in and this state coming in? The same P. That's right. And RT and ST. And here, the argument has to be previous ST minus 1 and AT minus 1. So the claim is that this gives you a probability distribution over history. So if you sum this up for all possible values of HT, well, you get 1. The numbers are between 0 and 1 for sure. And you can check it for yourself so that this is well defined. I mean, like, I could come up with like arbitrary numbers multiplied or maybe added or whatnot. And then you don't have to believe me that it's a probability distribution. You can verify whether it's a probability distribution. So this, okay. So small, this table, or whiteboards. Okay, we don't need this. You remember this obligatory picture your hat? I like it. So if we sum this up for all HT, in capital HT, we get 1. So P, so from this, it follows that P is well defined. And there is a theorem that's called Kolmogorov's extension theorem. Thanks, Kolmogorov. That says that we're still good in the infinitely long sequences because these are consistent, like between each other, they're consistent, these definitions. So that means that if you're kind of like taking the total law of probability for, you know, t plus 1, and you're summing over the last bit of it, like the last action and reward and next state, then you get the previous definition, so they're consistent with each other. And then Kolmogorov guarantees us that this can be extended up to infinity. Why do we extend this thing to infinity? It's because the book loves this infinity, right? Like we're summing up all the rewards up to infinity. And so how do we do that? We need a probability distribution over these infinitely long sequences. Can we get that? Thanks, Kolmogorov. We can. Okay. So good. So now we have P. If you have P, you have E, right? So when the book is writing a lot of E's, it means the expectation with respect to a probability distribution like that. But you have to notice here something. And the thing to notice, everything is useful on this board. So P was a function of 3 different things. It was a function of mu, pi, and little p. Why change any of these things? Definition of P changes. Should make sense, right? Like the probability of saying whatever, like it depends on what policy you choose. It depends on which MDP you are. It also depends on the initial state, right? So when people write just P or E, they rely on your goodwill of guessing what I mean. Which of the mu, which of the pi, which of the P. The P is kind of fixed most of the time, except until very late when we're talking about that, oh, I want my algorithm to work against all these MDPs, different swapping MDPs under my algorithm. So I have the same policy, history-dependent policy, and I want to show that it works no matter what the MDP is, then like you're changing the MDP. But until that moment comes, and it will come so long, P is fixed, so we're going to not denote it, like not show it. So it's kind of like, yeah, we just, if we want to emphasize this dependence on initial distribution and the policy, then we write just P of mu and pi. And then if mu is understood, then maybe just write P of pi. And we will never write P of mu, I think. That doesn't happen. Because pi is kind of important. If you don't write anything, then you have to explain to the reader, what is the pi underlying? And maybe the text does it, right? Like you read the text a little bit before and like, okay, goodwill. That's how you have to read these things. So one more notation that you will see very, very frequently in reinforcement learning texts is people write a P or an E and something here, I don't know, like the probability of some state 5 being 3. And then they start to write things like that A naught is sampled from pi S naught because they have, I don't know, memoryless policy, and A1 is sampled from pi S1 and so forth after the bar as a condition. But if you read probability theory, there is no such thing as like this tilde in a condition. So what do they mean here? They can't possibly mean anything else than this notation. So it's just like you put this into the condition, like that's a prescription of like how the probabilities to the actions are assigned to a in this process, right? It's the same notation. It's the same idea. I mean, the notation is obviously not the same, but they want to, rather than introducing something like this and then saying that, oh, it depends on pi, and so whenever I write pi in the index, this is what I mean, like this thing here. They just write it after the conditions. It's constructed on the fly, and the reader should understand that it means the same thing. Okay? Some people even would write things like that ST plus 1, RT plus 1, and ST plus 1 is sampled from this little probability kernel, by which they mean the same. It's just like part of the definition of this P. So they are, it's an inline definition of the symbol that you're using. It's like syntactical sugar. Okay? Yeah. Not really a problem if you understand it well. It becomes a little bit murky if you write things like E naught equals pi S naught. For example, pi was deterministic. So let's say the author says, we have a deterministic policy. So in the condition, I just write A naught is computed by P S naught. So if you write equality, in mathematics, equality is a relationship. It's not an assignment. So here, this was an assignment. So this is a command that the probability distribution should be done this way. So here, it's a little bit unclear whether this is meant to be an assignment. So if you just see this, like that's a little bit unclear what it means. I wish then people would write something like colon equals or something like that. Or they would just, write it in the index that like policy pi is used, and the distribution that is induced on histories by using policy pi in this MDP M or P is what I mean here. Okay. Which one? Which P? This P? This P? Bottom, this one. You shouldn't use this notation if you have a choice, because it's like, unless you introduce what you mean. If it was up to me, I would introduce, like, if I really wanted to use, I would define it clearly to mean that after the bar, you can write these tilde things. And if you write the tilde thing, that the constraint on the sampling distribution of the variable here coming from this distribution independently of everything else that is not mentioned here. So for example, here, only S1 is mentioned. So that means that it's not just the marginal of A1 is equal to this. It's not just like given S1, this is what we have. But like given all the past information, the distribution of A1 should be coming from this distribution. So it's like a lengthy explanation. So if you have a choice, just don't do it because it's just like non-standard notation. But okay, it's not the end of the world if someone does it, right? Like we sort of understand what the meaning of it wants to be. But I don't want to spend time on, defining a new language of probability theory with this symbol, the load, and like, it's just too much for this class. Like if I was, I don't know, writing a tutorial, then maybe yes, but not here. Okay, but it's just because in papers you will see this happening. But then you know that they mean this distribution is what's coming from interconnecting the policy with the MDP. And it's defined very clearly here. Okay. Good. Almost there. 2 minutes. Yeah. So the reason I'm telling you all of this is because the first formula in the book is the value function of policy pi, and pi here is a memorized policy, whatever, is defined something like, so on the right-hand side, you see some t's in like, okay, yeah, I think that gt given, I don't know, st equals, or gt plus 1, then that's gt. And st equals s. And so that's the definition of the value assigned to state S if you're following policy pi. I have a little problem with this as a mathematician. And my little problem is that to define a conditional probability, the condition needs to happen with positive probability. If it doesn't happen with positive probability, then conditional probabilities and conditional expectations, for that matter, are kind of ill-defined. You can define them arbitrarily. So you can see that this is pretty troublesome because this policy may be so that at time step t, it has no chance of visiting little state S. In which case, even if I would understand that, okay, there should be a pi here, because it's like left-hand side is dependent on pi. Maybe the right-hand side should also depend on pi. Okay, fine, let's just suppress notation. But if the condition happens with zero probability, then I don't know what this means. In mathematics, no meaning is assigned to it, or you can assign arbitrary meanings to it, but this is being used as a definition. So the big showdown or whatnot, like, okay, what's the correct definition for this? Well, today we introduce all this beautiful notation. So very simple definition for this is that you take as mu the distribution that puts probability mass of 1 on state S. Okay, so this is just the indicator that S equals S prime. Oops, sorry, man. And that's your mu. And then V pi of S is going to be the expectation of O. So we have the initial state distribution here. So let's call it mu S. So we have the probability distribution defined here based on the policy, based on the initial distribution. Let's choose the initial distribution that it puts a probability mass of 1 on this initial state. And then let's look at what return we get from that point on. There is no conditioning. The conditioning is done by the initial state distribution. You imagine that the process starts at that state, and you ask, what would be the total return on expectation that I would get if I follow the policies through? That's it. No conditioning, no problem. That doesn't mean that conditioning is completely useless, but you just have to be careful when you're using it for definition. So we can't. So we use this definition. We'll have a similar definition for Q pi and the other things, and we go from there. Like we build up, like why do we have these Bellman equations and whatnot? So no, we can go home, think about this, and come back on Wednesday. We'll discuss it further.